All right, now we'll learn a little bit about potential energy, the other basic type of energy. Again, every form of energy in the universe can be broken down into either kinetic energy or potential energy. Doesn't matter what it is. They are the two basic types of energy, the two big categories of classification. The definition for potential energy that I use is energy of position. Oftentimes you'll hear it described as stored energy, but how do you see something that's stored that you can't see? Again, remember, energy is intangible. When an object has energy, it doesn't look any different than an object that doesn't. Think about two batteries. One is good, one is dead. If they're both sitting on a table there, you wouldn't be able to look at them and tell which one is which. You couldn't put them on a balance and tell which one is which. The only way you would know which one actually had the energy in it would be to put them in a flashlight or something and see if they worked, to see if they could cause a change, because again, energy is the ability to cause change. You can't see stored energy. So with the type of energy we're working with, this definition works a lot better, energy of position, because while you might not be able to see the energy in an object, you can certainly see where it's at. And that's what I'm talking about here. We're not going to base our identification on what the object's doing, whether it's moving or not, like we did with kinetic energy, but where it is, its location or its position. Objects have potential energy anytime they are out of their resting position. Anytime an object is out of its resting position, it has potential energy. The resting position is just simply the place where it normally would be. Its natural place. That is its resting position, its normal location. We're looking at a type of potential energy called gravitational potential energy. Potential energy is caused by gravity. The resting position in this type of potential is the ground. So simply put, an object has potential energy, gravitational potential energy, when it's not on the ground. Again, that's functional. That's something you can see. That's something that you can identify. It works better than stored energy. This smart board has potential energy. And I know that because it's not on the ground. It's pretty simple. It makes it as simple as the kinetic energy identification. In kinetic energy, we're just looking for motion. If it's moving, it has kinetic energy. My smartboard is not moving. It has no kinetic energy. Using the definition of energy of position gives us the same equally easy way to identify an object with gravitational potential. If it's not on the ground, it has gravitational potential. And again, this smartboard is not on the ground. This time I'm using a tennis ball as my example. That tennis ball is sitting on the clay. That tennis ball is sitting on the ground. And because it's sitting on the ground, it has no potential energy. Any object that is on the ground has no gravitational potential energy, which I will abbreviate GPE instead of writing that word out over and over and over again. This tennis ball has no gravitational potential energy because it has no potential to fall. Simple enough. If a tennis player picks up that ball and holds it in the air, now everything's changed. Because he's holding it in the air, it's not on the ground anymore. And there's the potential he could drop it and it could fall. It has the potential to fall. It has potential energy. Again, gravitational potential, the resting position is the ground. If it's on the ground, it has no gravitational potential. If it's off the ground, then it does. There are three factors that affect gravitational potential energy. Mass is the first of those three factors, those three variables. And just like it was with kinetic energy, it's directly proportional to the mass. Mass and gravitational potential energy are directly proportional. And again, the word directly in front of this means they change in the exact same way. We're thinking about mass as the container for energy again. As I mentioned in the kinetic energy video, matter and energy are two different things. Matter is the physical part of the universe, the stuff with mass and volume, the stuff that you can touch, taste, smell, manipulate. That's physical. This is matter. I can pick it up. That's how I know it's matter. Energy is intangible. It's an ability. So you can't see it, you can't touch it, you can't taste it, you can't smell it. You can only see what it does to matter. Again, think about the battery example I just mentioned. If you've got two batteries on a table, one's good and one's dead, you wouldn't know which one is which until you put them in a flashlight and try to turn it on. The one that has energy will cause a change. It'll cause the light bulb to light up. They can be together. Matter can be a container for energy. That tennis ball, when it's sitting on the ground, is an empty container waiting to be filled. When the tennis player picks it up, that act of picking it up fills the tennis ball with potential energy. Mass tells us how big the container is, how much energy we can dump into it. The more mass you have, the bigger the container, which is why mass and gravitational potential are directly proportional. An object with more mass has more capacity for energy storage. You can put more energy into it. And again, we can think about the battery example as a perfect example. AAAs, AA's, C cells, D cells, they're all the same battery. They're all 1.5 volts. You could literally use a AAA battery to power anything that uses a D cell battery. Problem is, it wouldn't last very long. It's about capacity. The AAA battery is very small, has very little mass. The D cell battery is a whole lot bigger and has a whole lot more mass. So the AAA battery holds much less potential energy than the D cell battery does. So the AAA battery wouldn't last very long in a device that used D cells. Flipped it around and used a D cell battery to power something that uses AAAs, it would last a whole lot longer. Think about it that way in terms of mass. Here in the picture there's a bowling ball and a bunch of feathers that are suspended from a ceiling. They're both at the same height. But we would say the bowling ball has more gravitational potential energy because the bowling ball has more mass. Think about the act of getting them there. Lifting the feathers and the bowling ball to the ceiling and putting them on those little racks that they're on. It'd be really easy to lift the feathers up and put them up there on the rack. You wouldn't have to use a lot of force, which means you wouldn't be putting much energy into those feathers. But to get the bowling ball up there, you'd have to put a lot more effort into it. You'd have to use a lot more force to pick that bowling ball up and put it up on the ceiling. And because of that, it will be storing more energy. Again, it's directly proportional, so doubling the mass would double the gravitational potential energy. Cutting the mass in half would cut the gravitational potential energy in half. It's the exact same relationship we had with kinetic. The second factor is height, because obviously the position is off the ground. And the further off the ground it is, the more potential energy it has. And again, it is a directly proportional relationship. Height and gravitational potential energy are directly proportional. When we talk about kinetic energy, we talk about velocity being the indication of how full the container is. Here, height is how full the container is. If I take something and just lift it a little bit off the ground, I have not filled it up very much. I have not put much potential energy into it. But if I lift it way up into the air, I have filled it up with a lot more gravitational potential energy. So think about mass as the size of the container. Think about height as how full it is. In my illustration here, I have a yellow skier at the top of a ski jump. I have the blue skier at the top of a ski jump. The yellow skier is lower than the blue one. If they are both equal in mass, the blue one would have more gravitational potential energy because they're higher up. If their height was 20% higher, it would be 20% more gravitational potential. If they're 30% higher, it's 30% more. It's directly proportional. Again, directly proportional means they change in the exact same way. So doubling the height would double your gravitational potential. Cutting it in half would cut your gravitational potential in half. The third and final one that we don't see very often, but again, since we're talking about lifting things off the ground, and since we're talking about gravitational potential energy, is going to be gravity. And the reason why it ends up being overlooked is because we don't often think about the gravity. It's everywhere, and it doesn't really change any, so we kind of take it for granted. We are talking about gravitational potential energy, so it is one of the three factors that will affect it. Gravity and gravitational potential energy are, again, directly proportional. This is an easy one. They're all the same. You have mass, you have height, you have gravity. They are all directly proportional, which means they all change in the same way. Gravity is the force that's actually causing the object to fall when we let it go. Gravity is the reason why it has gravitational potential energy in the first place. So it makes sense, the stronger that gravitational pull is, the stronger or more gravitational potential energy that object would have. And again, we don't think about it much because when's the gravitational potential energy going to change? And the answer is, on Earth, where you're at, it won't. But this is physics, and physics is universal, which means we don't even have to stay on Earth. So if you were doing the same kind of calculation, the same kind of problem on the moon, your results would be different because the gravitational potential energy is different. This is a video clip from NASA of astronaut David Scott on the moon. And he is dropping a feather and a hammer. And this video clip is used a lot when we teach free-falling objects and how all objects fall at the same rate regardless of mass. We don't get to see it on Earth very much because of the atmosphere. So what David Scott did the experiment on the moon, where he dropped the feather and hammer in a place where there was no atmosphere. They fall at the same rate and they hit the ground at the same time. I'm throwing this up here so you can see how slow that hammer falls. If you drop that hammer while you were working on something and it was falling on the moon, you kind of have plenty of time to move your foot out of the way before it falls on your toe. On Earth, that wouldn't necessarily happen. If you dropped the hammer and your foot was underneath it, it's probably going to hit your toe and it's probably going to hurt. But on the moon, if you watch how slow this hammer falls, you would legitimately have time to get out of its way because it falls much slower than it does on Earth. And the reason for that is the gravity's less on the moon. It's about 83% lower on the moon than it is on Earth. And because that gravity is 83% lower, the potential energy is 83% lower. So even if this thing hit your toe, it wouldn't hurt nearly as bad as what it does on Earth because it has 83% less gravitational potential energy than it does on Earth. Last thing I'll mention before we get into the math is we have three factors. We have mass, height, and gravity. Sometimes we combine the mass and the gravity together. If you think way back to when we first started talking about forces in Newton's second law, weight is mass times gravity. So what we sometimes do in our calculations is we ignore the mass and the gravity and we just look at the weight of the object. Because mass and height, when multiplied together, or mass and gravity, when multiplied together gives you weight, we can simply look at weight and height as two factors that affect gravitational potential energy. And again, the relationships are going to stay the same. They're all directly proportional. If I take two variables that are directly proportional and combine them together, the new one's also going to be directly proportional. So I could say height and gravitational potential are directly proportional, and weight and gravitational potential are directly proportional. So you will see it times like that, you will see it simplified, so don't be surprised. It does give us two different equations that we could use. This first one has all three variables in it, mass, height, and gravity. Usually it's written as mgh. Mass times gravity times height, they're all multiplied together because they're all directly proportional. This is the simplified one. This is where we take the mass and the gravity out and replace it with weight. Unit-wise, this is still going to be in joules. So just like in kinetic energy, that's got to be kilograms, that's got to be meters per second squared this time, because that's acceleration. And that's got to be in meters. kilograms, meters per second squared, meters. If we're working with the second equation to get joules for our answer, weight would have to be in newtons. Newton, if you remember back to Newton's second law, that's the unit we use for forces and weights. Newtons, and that has to be in meters. So kilograms, meters per second squared, meters, if you're using the first equation. Newtons and meters if you're using the second equation. And when you do that, you'll end up with joules for your gravitational potential energies. All right, let's take a look at a problem. Since my battery's probably getting close to dying, I will do the one that's most complicated. All right, I have a 10-pound bowling ball carried to the top of a 25-foot tower held over the edge. You've seen the videos on YouTube where they're dropping stuff on trampolines and stuff to see what happens in slow motion. Not an unreasonable thing to find there. 10 pounds is actually a unit of weight, but not the unit of weight we need. If we were doing weight, we'd need newtons up there. So we know we're going to have to convert this. This is not going to work for us. And I've given us equivalents that we can use over here. I have to correct this like I did in class, because this is a picture, not typed. 1 kilogram equals 2.2 pounds. That's the equivalence that will allow us to convert this into a unit that we can use. We can't just move a decimal point around this time because it involves an English unit. We actually have to do the math. Again, we start with the number that we're given, 10 pounds, times and then a fraction bar. We take the pounds out of our equivalents over here. That would be the 2.2. We take the kilograms and put it on top. And again, what we're doing is we're looking to see where the 2.2 ends up. If the 2.2 ends up on the top, we're going to multiply by it. If it ends up on the bottom, we're going to divide by it. So it ended up on the bottom. This is 10 divided by 2.2. That's 4.5454 repeating. We're just going to round it to 4.5. Pounds would cancel out, and that would be kilograms, which is what we need, which is what we can use. This process is called dimensional analysis. You should have learned it in honors chemistry. It's a huge part of stoichiometry. The other number we're given here is 25 feet. And while 25 feet is a legitimate unit for height, it's not metric. And to get our answer to be in joules, it's going to have to be in meters. So we'll use the second equivalence. 1 meter equals 3.28 feet to do that conversion. Again, we start with the number we're given, times and then a fraction bar. We look at our equivalents. We look over here. We have feet as our given, so our feet have to go on the bottom. The 1 meter would go on top. And again, it's so we can cancel those feet out and get meters, which is the unit that we want. We look to see where the 3.28 lands. If the 3.28 lands on top, we're going to multiply. If it lands on the bottom, we're going to divide. So this is going to be 25 divided by 3.28. That's 7.6. And yeah, it ended up being divided by both times, and that's only because of the equivalences I gave you. It's not always divided. Again, you really have to look at where that number lands. If you want to see one where you multiply, go back and watch the kinetic energy video. Once we've done that, now we can calculate. We have our mass, we have our height. We know that 9.81 meters per second squared is gravity. We can find our gravitational potential energy. Gravitational potential energy equals mgh. It's mass, which is 4.5 kilograms, times gravity, which is 9.81 meters per second squared. And we have our height, which is 7.6 meters. So 4.5 times 9.81 times 7.6 is 335.5. This is kilograms times meters, that'd be meters squared, over second squared. Kilograms times meters squared over second squared is joules. We need kilograms, meters per second squared, and meters to get there. Not going to do an algebra one because, again, I think my battery is probably close to being dead. The algebra here is relatively simple because everything's just multiplied through. There's no squaring this time. There's no fraction this time. So if you can do the algebra on the kinetic energy one, you can do the algebra on this.